Hello guys, welcome to Concepts of Physics with Irfan. So guys, today we are going to continue our video lecture on vectors. Last time we defined and explained the different way to represent vectors. So today we will be looking at unit vectors, and we will be also discussing how to add two vectors. So before we will define and explain unit vectors, let us review that vectors are such physical quantity which can be represented by magnitude and direction, right? Plus a direction. Now, mathematically we can represent this statement as, let's take a vector A, and this vector in terms of its magnitude can be written as A absolute times, and for direction we use a special vector which we call as unit vector, and that unit vector is represented by a letter and a cap on that letter. So a cap or a hat is actually representing unit vector. Okay, so unit vectors. Okay, before I define unit vectors, I would like to explain an alternative concept that actually provide a ground in order to understand the concept behind unit vector. So let us take natural numbers, and if we add such natural numbers, like we can take any example 2, so we can represent that 2 with another natural number, that is 1. So when we add 1 and 1, we will get 2. So we can write that it is twice of 1, right? In the same way, if we take another example 3, so we can write 1 plus 1 plus 1. So 3 can be expressed in this way, and this is actually 3 times of 1, right? So in the same manner, if we are having a vector, and let's call that vector as R, and this vector R has a magnitude and a direction. Now if we break this vector into equal pieces in such a way that each component or each small piece of that vector will be having unity magnitude or one magnitude. So let's say that if let us call this as R prime. So R prime magnitude, if it is 1, and all these are equally spaced vectors, so they all be having the same magnitude unity. So at that time, these small vectors, they will be only representing the direction of the original vector because they have unit magnitude, right? So such vectors which is used to represent the direction of a vector is called as unit vector. So it is a vector having magnitude of unity, or one magnitude, right? So it only gives us an idea about the directions, right? It gives the direction, and you can see from this equation, let's call this equation as A. So from equation A, we can write that a vector A is written in terms of its magnitude and unit vector. So this unit vector AK can be written as vector A divided by magnitude of A. Now from here you can see that a vector is having a magnitude and a direction is divided by its own magnitude. So over here the magnitude are going to cancel one another, so we are only left with a unit magnitude, or we are only left with direction, right? So that's why we can say that a unit vector is dimensionless. So it is dimensionless. So it has no unit, right? Okay, so so far we discussed that unit vectors are such vectors which are used in order to represent the direction of a vector, and we can find out a unit vector by dividing a vector by its magnitude. Okay, further, if we represent a vector in a reference frame, and at interlevel or at FSC level we use Cartesian coordinate system. So let us take a three-dimensional Cartesian coordinate system. So x, y, and along the space we are having z, right? So we are having three-dimensional Cartesian coordinate system. So this is the z-axis. Okay, now if we represent a vector on such a three-dimensional Cartesian coordinate system, then there are some special unit vectors, predefined special unit vectors, and those unit vectors actually define the direction along any particular coordinate axis. So we are having three axes, x, y, and z. So if a vector is totally along x-axis, let us use the blue one. So let us take that we are having a vector and the vector is pointing along positive x-axis, right? So now whatever magnitude it has, we are not interested in its magnitude. Now the direction for such a vector can be represented by using a unit vector, and that unit vector is what we call I k. Similarly, if a vector is along y-axis, then the unit vector which shows its direction is j cap, and a vector along z-axis will be having a unit vector k cap. So there are fundamental three unit vectors: I cap along x-axis, j cap or j hat along y-axis. This is along x-axis, okay, y-axis, and k cap along z-axis. So we will be using these unit vectors in our upcoming lectures. Okay, so we can write a vector in terms of its unit vector I cap, j cap, or k cap, right? Okay, now next we will be discussing that how we can add to addition of vectors. Let us consider an example. If we are having a block, right, having some mass and it is lying on the floor, right? So two students were applying force on this block. One is in that direction and we call this force as F1, and another student is applying a force in that direction. We call this force as F2. Now this block, it is not going to follow either any one of these directions, and it will in turn it will follow a new direction. What does it mean? And this direction or the resultant force appear in this direction is what we call resultant or net force, right? So whenever we apply force in different directions, as a result of such forces, a new force actually developed at that particular situation, and that force will be following a totally new direction. And this is because the net effect of such a force are going to add following vector algebra. So now we are going to discuss that, okay, in such a situation, how we can find the resultant force, both its magnitude and direction, right? So for that, we are having a rule, head to tail rule. So applying head to tail rule, we can find the resultant of two forces or two vectors, and this rule states that two vectors can be added, two or more vectors. So let us take two vectors can be added by placing tail of second vector on the head of first vector, and then joining the tail of first with the head of last, or with the head of second in this case, with the head of second vector. Okay, right. So let us take those two forces. One force is in this direction, F1, and another force is in that direction, F2. So in order to add such two forces, we have to place the tail of the second vector on the head of first vector, right? And then we have to join the tail of first vector with the head of last vector. So this would be the resultant. But you know, in order to express vectors in terms of their magnitude and direction, we need a reference frame, and that reference frame is what we discussed, in our last lecture, the Cartesian coordinate frame. Okay, now it's better to use an xy plane in order to add such two vectors. So let us say that this is our x-axis and this is our y-axis. Okay, now we can draw both these forces on this plane, right? And for that, this is, let's say, the origin. So the first vector must start from the origin. So let us draw F1, and this is F1, making certain angle theta with x-axis. So that's why we need a Cartesian coordinate system in order to express its direction in terms of theta, right? Now, according to head to tail rule, we have to place the second vector in such a way that its tail must coincide with the head of the first vector. So for that, over here we are going to draw a kind of virtual x-axis. So that x-axis will be parallel to this original x-axis. Okay. Now from here you can join the second vector, that is F2, in such a way that it will be making an angle of theta 2 with the virtual x-axis, right? Okay. Now we can join the tail of first with the head of last vector. So this gives us the resultant vector r, and this vector, resultant vector, is making an angle theta r with the x-axis, and you can see from here. So the resultant vector r will be equal to F1 plus F2. Okay, and one important thing about vector addition is it follows commutative property. So it commutes. What does it mean? So it doesn't make any difference whether we draw F1 first or F2 first. So the result will remain the same. So we can write that R resultant is equal to F1 plus F2, and that is equal to F2 plus F1. So you can see if we draw F1 first and then we draw F2, the resultant will remain the same. So let us draw F1. So let's say that this is F1, okay, right, making an angle theta 2, F2, sorry, F2 making an angle theta 2 with the x-axis, and then over here at the virtual x-axis we draw theta 1, F1. So F1 will be this one. So again you can see we are going to get the same resultant vector r, right? So that's why vector follow commutative property. Okay. Now let us define another special vector, that what we call null vector. Null vector. So it is such a vector having zero magnitude, and arbitrary direction. Okay. So if it has zero magnitude, so why we need such a vector having no magnitude, right? So the reason is most of the time while operating two vectors, we such vectors which cancel one another, at that time we have to avoid zero value. So instead of zero we can use null vector. Like if we add two vectors, let's say this is the vector A. Now if we multiply such a vector with a negative sign, then it becomes negative of A, and negative of A is the same vector as A, the only difference will be of its direction. So these two vectors will be anti-parallel. A vector and a negative vector will be anti-parallel, right? So if we have such two vectors, A plus into minus A, then these two vectors are going to cancel one another. So instead of writing 0, we can write here null vector, right? So null vector. So this is what we call negative vector. Negative of a vector. So whenever you will multiply a vector with a negative value or minus 1, at that time the magnitude of that vector remains the same, but it only changes its direction, right? Totally. Okay, students, in the next lecture we will be discussing component of vectors and resolution of vector. Like we can break a vector into its component or into its parts. Okay, so I hope you will stay tuned, and if you want to watch more videos, subscribe this channel. Today's video lecture is dedicated to all those women who are pursuing degree in physics. Happy Women's Day.